So for this Hess's law problem, we want to make sure that this equation that's up here is what all of these down here look like. So if there's a hydrocyanic acid on this side, I need a hydrocyanic acid on this side, and this side I'm talking about the arrow. So there's an NH3 here, but it's on the product side. I need it to be on the reactant side, so this equation needs to get flipped around. So I will flip it around. Let's cut this, Control X, Control V, and then when we do that, we have to change the sign to positive. We also have another problem, that there's only one ammonia here, and I have two ammonias here. So since that's the case, what I need to do here is reduce everything, divide everything by 2. So I'll divide this by 2. That gets canceled out. I'll divide this by 2, which makes this a half. Divide this by 2, which make that 2/3, and I have to divide this number by 2. And so then we'll end up with like 45.5 or something like that. Okay, so this equation looks good. So I've got this guy right here, and I've got one of these guys right here, so that's good. We're going to end up needing some hydrogens over here, but that nitrogen thing's going to have to disappear. All right, so next thing I want to do is I need this methane. This methane needs to be flipped over on the other side, so let's go ahead and do that. So I'll flop this, Control X, Control V, Control X, Control V. And so since I flopped that, I got to do the same thing over here and make this positive. And let's see, it looks like the number's the same. I've got one methane and one methane, so all that looks good. So right now, it looks like we got 3.5 hydrogens, and we're going to need 3. So it'll probably work out over here. So here's 2 hydrocyanic acids, and I only need 1. So I'm going to have to go ahead and divide this by 2. Wrong pen. So divide this one by 2. Oh, I need to change this pen. We'll just do red just for the heck of it. So if I divide this by 2, that goes away. And this becomes a half. Divide this by 2, that 2 goes away. And then divide this one by 2, and it gets me pushing on the keyboard. And I divide this one by 2, and we end up with a half. Okay, so is that right? All right, so what we got here is I need to have a methane. So there's a methane, and there's my methane on the right side. I already took care of my ammonia. I need hydrocyanic acid, so there's one right there, and there's one right there. And so now what I need is 3 hydrogens. So do I have 3 hydrogens? So I want 3 of these guys, and what I have here is 1.5 and 2, so that gives me 3.5, but I have a half over here, so then this half will cancel out with that half right there, and I'll end up with 1. There'll just be 1 hydrogen here, and so then that 2 and that 1 gives me my 3. Oh, I forgot something. We forgot to, divide by 2. Got to divide this guy here by 2 because we divided through by 2. So let's see what the math looks like. Looks like 91.8 divided by 2 plus 74.9 plus 270.3 divided by 2, and I get a positive 255.95 kilojoules per mole. So that gives us a total, looks like 3 sig figs is all we have. So this would be 256 kilojoules per mole. Okay, next one. Well, the the heat of vaporization for water is 540 calories per gram, and the heat of fusion for water is 80 calories per gram. So the vaporization is how much it costs to turn it into a vapor, or how much you get if you go from a vapor to a liquid. And this is how much it costs to melt ice, or how much you get back if you go from liquid water into ice. So obviously it's going to take a lot more energy to vaporize the water. So how much more? So I've got 10 grams and 80 calories per, did that upside down, sorry. 10 grams and 80 calories per gram. So that's 800 calories to melt, and then it's 10 grams, 540 calories per gram, and then it's 5,400 calories to boil. And so then if I just subtract off the 800 calories, the difference is 4,600 calories. So it's going to take 4,600 more calories to vaporize the ice than it is to melt the ice, 10 grams that is. So this next one is about heating curve, and our heating curve would look something like this. So this would be heat. Nope, that wouldn't be heat. This would be temperature, and then this would be heat added. And so our curve kind of looks like this. And the flat parts are where I'm in a phase change, and the angled parts are where I'm increasing molecule movement. So making ice move faster, making water molecules move faster, making steam move faster, melting it and boiling it. Okay, so we're going to have to do 5 different calculations. So let's go ahead and start. We're going to take this ice that's at negative 52 degrees, and we're going to raise its temperature up to 0 so we can get it to its point where it can begin melting. So Q1, and it's 250 grams, and it's 0.5 calories per gram degrees C. This is the specific heat for ice. It would be something that you would be given on a test, or you could look up, and it's the change in temperature is 52 degrees Celsius, because we take it from negative 52 up to 0. If I do that, the math is 250 times 0.5 times 52. I get 6,500 calories. So this 6,500 calories corresponds to this part of the curve, and all of that is being used to move H2O. Well, let me change that. I'll have it. The molecules of water are moving faster. Okay, so the next thing we want to do is melt it. Okay, so the next thing we have to do is calculate how much energy it's going to take to melt this. So it's 250 grams, and it's 80 calories per gram. So the gram units cancel out, and we have, what is that, 10,000? I think that's 10,000. Right? Let me just make sure. Nope, can't do math today. 20,000. So, what is this 20,000 calories for? This 20,000 calories is being used to melt. So that's breaking connections. Breaking connections between water molecules. Okay, let's do Q3. So this will be, again, 250 grams, and the specific heat for liquid water is 1 calorie per gram degrees C, and it's 100 degrees for the temperature change, 0 all the way up to 100, and so we end up with 2500 calories. And this energy is being, all of this is being used to heat the water up, so make them move faster. So each of these angled sections is making the water molecules either vibrate faster or rotate over the top of each other faster or fly through the air faster. And then Q3, nope, sorry, 4. This is the boiling part. This is the most energy intensive portion. So my 250 grams. And then I've got, how much here? 540 calories per gram. And this is 135,000 calories. So the energy needed to boil is more than all of the other energies added together. So this is just this boiling portion right here. So this is to boil, and this is to break all connections. Because what we're talking about is turning it into a gas, so now the water molecules are no longer touching each other. And we got Q5, and so the last thing we'll do is we'll just heat this up from 100 to 28 degrees. So 250, and then again it's a half a calorie per gram degree C for steam, and I'm going up 28 degrees Celsius. So 250 times a half times 28, and that's 3,500. And this energy is being used to make this water move faster. All right, so then the answer for this is going to be my 6,500 plus 20,000 plus 25,000 plus 135,000 plus 3,500, and that's 190,000. So if I add all of these guys up, I end up with 190,000 calories total. So that's to go from this part right here all the way up to this part right here, if this is 128 degrees Celsius and this is negative 52 degrees Celsius. That's it.